So if you're like me, you've always wondered, is there any connection between complex number multiplication and the complex plane? Now before we dive into the answer, we need to give a brief explanation of where complex numbers even came from. Long ago, the only numbers that seemed useful were the natural numbers, 0, 1, 2, 3, and on. But when we realized that it would be useful to be able to have numbers that are non-whole numbers, like 1.5 cups of flour or the distance around a circle, these numbers fell between the natural numbers and are now known as the rational and irrational numbers. And all was well till we realized that you can't subtract 3 from 2, and long story short, we discovered negative numbers. Negative numbers sit behind the natural numbers, and the natural numbers plus the non-whole numbers plus the negative numbers gave us the real numbers. So what about our complex numbers? Well, we couldn't take a square root of a negative number. The square root of a number just says what number times itself equals this number. The problem with that is that no number, positive, negative, or non-integer number, when multiplied by itself is equal to a negative number. And so the square root of a negative number does not have an answer. But these numbers, which are the square root of negative numbers, turned out to be pretty useful. So the imaginary numbers were discovered, which are the square root of negative numbers. For example, I times itself equals -1. And the imaginary numbers plus our real numbers give us the complex numbers, and they live on the complex plane. Now back to complex number multiplication. Complex number multiplication is just multiplication using the distributive property. For example, 1 plus I times 2 plus 3i is equal to 1 times 2 plus 2 times I plus 1 times 3i plus 3i times I, which is equal to -1 plus 5i. Now back to the question at the beginning of this video. Does this have any connection to the complex plane? Well, it turns out that the answer is connected to polar coordinates and e to the I pi. Polar coordinates are a two-dimensional coordinate system where instead of x and y components, we have a distance r and an angle theta, where r is the magnitude from the origin and theta is the angle from a reference direction. This coordinate system can be used for complex numbers as well. For example, you could write 1 plus I as a magnitude of the square root of 2 and the angle of pi quarters in polar coordinates. Now for the e to the I pi. I will not be proving that in this video, but I will leave a link in the description made by 3 Blue 1 Brown that proves this amazing fact. But what it's basically saying is to walk pi radians around the complex unit circle and you'll end up at -1. The general formula is r times e to the power of I times theta, which says to walk around the complex unit circle theta radians and multiply our magnitude by r. Sound familiar? This is just what we were talking about with complex polar coordinates, and since any complex number can be written in polar coordinates, any complex number can be written as r times e to the power of I times theta. So when you multiply two complex numbers together, r1 times e to the power of I times theta 1 and r2 times e to the power of I times theta 2, you get r1 times r2 times e to the power of I times theta 1 plus theta 2. This means when you multiply two complex numbers together, their magnitudes multiply together and their angles add together. This is the answer we were looking for at the beginning of this video, but what does this process look like for two actual complex numbers? Say, for example, you have two complex numbers and you want to multiply, say, 1 plus I times 2 plus 3i. Instead of using the distributive property, you can find their angles with some trigonometry and their magnitudes with some Pythagoras, add the angles, then multiply the magnitudes, then use some more trigonometry to find the real and imaginary components of your answer, and done. -1 plus 5i. Also, to divide complex numbers, instead divide the magnitudes and subtract the angles. This is also the answer to why when you multiply complex conjugates together, the answer is always a real number, but I will leave that one for you to figure out. And there you have it, the slightly more simple and visual version of multiplying complex numbers together. Thanks for watching.